Morning, everyone. How are we doing? Questions while we wait? Weekend was fine. Weekend was fine. Is the midterm ready? I think it is. I actually haven't looked at it though. I had one of the other instructors write it. Let's do this question, and it'll be a good. It'll serve as a good reminder of what we were doing last time. We have class every day from now on. I mean, by every day, I mean every day we're supposed to have class. So we have class, even though the midterm opens up on Friday morning, we're still going to have class. Now, we will not be answering any types of questions for that whole 72-hour period, unless there's an issue with the midterm, right? So, but I mean, we will not be answering any question about material during those 72 hours. So if you have questions if you have material you want me to go over before the midterm, we'll happily do that in class. Otherwise, we'll do new material. There was one of the other instructors, Sean, I believe, is going to do a review on Thursday. There will be details posted on the announcements on my courses. In fact, I think we were going to do questions, or he was going to do questions during the review, questions that did not make it to the midterm exam. Right, so we had a bunch of questions that we were debating on using or not. We made up the midterm with some of these questions, and then he'll do the other ones. So consider this. What is the question? We are looking for find dy dx. Right? You have an equation which implicitly defines y as a function of x. Right? I mean, there's no way for you to isolate y on one side and function of x on the other, but it implicitly defines y as a function of x. Let us assume y is a function of x and differentiate a whole equation with respect to x. What do we get? So implicit differentiation, this is what we were doing last time. The derivative of the exponential is the exponential times the derivative of the inside. Inside is a quotient. So quotient rule applies. VU prime, derivative of x is 1, minus U V prime, the derivative of y is exactly that, the derivative of y with respect to x, divided by v squared, derivative of the right-hand side, derivative of x is 1, derivative of y is precisely that, the derivative of y. So there it is. Now it's just, is there a mistake? Where, so the derivative of this, the derivative of u over v, v u prime, the derivative of x is 1, so it's y times 1, minus x times the derivative of v, minus u v prime, the derivative of y is dy dx, all over v squared. I think we're good. I think we're good. I think we're good here. Let's finish it up by isolating. I am teaching 141 next semester. I might have said that too quickly. I mean, I'm scheduled to teach it, but since everything is going to be online, we'll see. We'll see. We'll see what's going on with the COVID situation. We'll see what's happening there. So now we want to isolate. We want to isolate dy dx on one side, everything else on the other. So it's just the usual, right? Just a little bit of algebra there. Maybe we can bring the y squared to the other side and rewrite this as y e to the x over y minus x e to the x over y dy dx is equal to y squared minus y squared dy dx. Well, I mean, whoever is teaching, it's all good, right? We have a good group of talented instructors. So maybe we want to bring this to that side, that over there. So there it is. Well, I knew not everybody will agree with that. And factor out and divide, the usual. So dy dx is easily seen to be there it is. Well, we'll see after the midterm, right? Maybe everything will change. All right. How are we doing here? I want to say that the midterm is going to be very easy if you are comfortable with the material. Yeah. So this kind of stuff we were doing last time, right? Implicit differentiation. And we in fact, last time we used the idea of implicit differentiation to find the derivative of the inverse of the exponential, right? We found the derivative. Look, the final exam is, of course, always harder than the midterm by nature, right? By the nature of the final exam, everything is there. The final exam includes everything, whereas the midterm only includes like a third of the course, essentially. So the final exam contains a lot more material, so of course it's going to be harder. But in actuality, the questions themselves are not harder. It's just the fact that there's more material to cover. Well, Yaz is asking the good question, and that's exactly where I was headed. Right, last time we saw the derivative of the inverse of the exponential, namely the derivative of the log function. Now the question arises naturally, what about the derivative of the inverse trigonometric functions? And that's exactly what we're going to do right now. What is the derivative of the inverse sine function? First of all, before we tackle this, let's remember what this really refers to. You know the sine function. You know the sine function, and you know the issue. You know that it's not one-to-one. So this function does not have an inverse. However, if we restrict our attention to a good interval, then it does. Then it is one-to-one and it does have an inverse. What interval am I referring to? Well, the interval minus pi over 2 to pi over 2. If you restrict your attention to that interval, this is the function we're looking at, one-to-one, and thus invertible. One-to-one, and thus invertible. And so the inverse exists, and we call it the arc sine function. Everybody should be studying for the midterm. It's important that you're comfortable with the material. Of course, since it's open book, open internet, and everything, you don't have to actually memorize anything, but if you don't do anything to prepare, it's going to be difficult. So my suggestion is get into the habit, study for it as if it was an in-person midterm, right? Because you're in your first year of university, you have to develop these good habits, and you don't want. I mean, you know that the winter semester is online, but you don't want to enter second year coming in person, and then it's going to hit you like a ton of bricks if you haven't if you haven't developed the proper habits. You can open and close the midterm as often as you want during those 72 hours, during that 72-hour period. The important thing is to submit the exam before the 72 hours are up. I understand that it's terrible times, and I mean, you're not getting the full university experience, but let me tell you, the first year is usually the most difficult in university because you have to get accustomed to the pace, and you're not really getting that now. Maybe you are, it is going fast, but let me tell you, first year is always very difficult, much more so than it is now. Right, so you understand that we're going to restrict our attention to the interval -π/2 to π/2. So where was I going with this? All I'm suggesting is you should tackle this course as if it was an in-person exam, even though it isn't, right? Learn the good habits, lots of exercises from the book. That's really all you need to do. For one of my other classes, it's a 6.5 hour. Maybe I mentioned that in this course. It might have been a mistake if I did. You get the full 72 hours. So 9 a.m. Friday to 9 a.m. Monday. You can open it up, do some stuff, close it, go do other things, come back to it. It's fine. And you shouldn't stress over the whole 72-hour period. If you know your material, you'll do very well. So this is the function. This is sine x. We are restricting our attention to this interval. And we're looking for, right, so first of all, by restricting the attention of sine x to this interval, this function has an inverse, and we call it the arcsine function. CrowdMark is what we'll be using. You'll get an email from CrowdMark Friday morning. So if y is the inverse sine function, what is dy dx? That's the question we're going to answer now. And we're going to do that by taking sine of both sides. If you do the same to both sides, equality is maintained. And sine of sine inverse is just x. So you have sine y is equal to x. What are we looking for? We're looking for dy dx. Differentiate the whole equation with respect to x, assuming y is a function of x. So implicit differentiation and there you have it. So you should do all the work on paper. So pencil, paper, take a screenshot. Or take a picture and upload it. So the derivative of sine is cos times the derivative of the inside. And the derivative of x is 1. So dy dx is 1 over cos y. This would normally be fine, but remember that your function was a function of x. It was explicitly defined as a function of x. So can we rewrite this in terms of x? Well, you know that in the inverse function, the domain and range are interchanged. right? So here the y is actually the x in here. So you are restricting your attention to the interval -π/2 to π/2. And you know that in the interval -π/2 to π/2, cosine is positive. So this is actually the same as the absolute value, right? Because cosine is positive. And this is the square root of cosine squared. And cosine squared, you know to be 1 minus sine squared. And sine of y was x. So this is 1 over square root of 1 minus x squared. Very nice and slick. Could you have plugged in sine inverse of x for y? Indeed, but then the problem is you have cosine of sine inverse. And that's not immediately clear that this simplifies. And it does. It simplifies to exactly that. So we don't want that answer. We want the simplest form. And there it is. Let's repeat with tangent. If you have the inverse tangent function, what is dy dx? From here to there, sine of y is x. So I'm just replacing sine of y with x. You know that for the tangent function, once again, we have to restrict our attention to, in general, the function is not one-to-one. Why do we square my aim, normally, right, if the function was implicitly defined, this would be an acceptable answer. However, we had x explicitly as a function of x. So we're hoping that the derivative is going to be a function of x as well. And that's our goal here, rewriting it as just a function of x. So can we rewrite cos y in terms of x? And there it is. Right? Inverse tangent, you know what's happening. The function is not one-to-one. But if you restrict your attention to the interval -π/2 to π/2, then it is one-to-one. Right? So if you restrict your attention to this part, the inverse tangent exists. So y is arctan of x. We'll do the same trick. We'll take tangent of both sides. And tangent of arctan is just x. So we have tangent y is equal to x. Differentiate the whole equation with respect to x, assuming y is a function of x. The derivative of tangent, you know what it is. Derivative of tangent is secant squared times the derivative of the inside. Chain rule. Thank you. Derivative of x is just 1. Bring the secant squared to the other side. We get dy dx is 1 over secant squared of y. You know. What do you know? You know that sine squared plus cosine squared is equal to 1. So if you divide by cosine squared both sides, we get tangent squared plus 1 is secant squared. So secant squared is 1 over tangent squared plus 1. And tangent y was once again x. So this is 1 over x squared plus 1. Very nice. So we did inverse sine, inverse tangent. Let's consider the inverse secant. Inverse secant, and you know the graph of secant. You know the graph of inverse secant. And we discussed that in the beginning of the course. And I suggested to you that in order to define the inverse secant function, there wasn't a convention in the mathematical community, right? Some people will take these two pieces, right? They'll take secant from 0 to pi over 2, and then pi over 2 to pi. So these two pieces to get an injective function. And some people will take the interval 0 to pi over 2, and then pi to 3 pi over 2. As our book does. And there was no reason given as to why that is, but now we'll see the reason for that. I suggested that the reason was the same as the reason why radian measure is more desirable than degrees. And as we saw in class, the reason is that the derivative is simpler. And here the derivative will be simpler if you take these two intervals, rather than these two. Let's see that happening. We have y equals the inverse secant function. First of all, let me be very clear. Don't let this notation confuse you. This does not mean 1 over secant. You understand that it's the inverse secant function. Ali's asking which intervals are we taking. Let's postpone that for the moment. Right now, in the beginning, it actually doesn't matter which interval we're taking, but we'll make it clear in a moment. Right, so you understand that secant to the -1 does not mean 1 over secant. Nobody uses that. Nobody uses this notation to mean 1 over secant. Nobody, including you. Take secant of both sides. And of course, the composition is once again x. So we have secant of y is equal to x. The usual, right? I mean, it's the third time we're doing this now, so I mean, you know what to do, right? We're going to differentiate the whole equation with respect to x, assuming y is a function of x. Implicit differentiation. The derivative of secant is, as you know, secant 10 times the derivative of the inside, derivative of x is 1. So dy dx is 1 over secant 10 there it is. Now secant of y is x. So if I can rewrite tangent y in terms of x, well, that's my ultimate goal. Can I rewrite tangent y in terms of x? Let's look at the tangent function. Y is inverse secant, so I mean, Michael is asking the question, was it no, Maxwell was asking the question, can we not just rewrite y as inverse secant x and you get tangent of inverse secant? Short answer, yes, but long answer, this simplifies. Tangent of inverse secant x simplifies. And how does it simplify? That's the real question. Why did secant y become x? Well, I mean, it says right here, secant of y is equal to x. My goal is to rewrite this whole thing in terms of x. Because originally, I had y as a function of x. So I'm hoping that the derivative will be a function of x as well. So what about this tangent y? Well, let's look at the graph of tangent x, right? You know what the graph looks like. And so on and so on. I mean, I'm not sure. Who knows? But there it is. What's the point? The point is, in the interval 0 to pi over 2, and in the interval pi to 3 pi over 2, tangent is positive. So if we restrict our attention to these two intervals, the intervals where tangent is positive, this tangent y is the same as absolute value of tangent y. Right? Tangent is positive there. And this is the square root of tangent squared. Tangent squared, I mean, I've rubbed it off, but I'm sure you can find it again. This is secant squared minus 1, right? Tangent squared plus 1 is secant squared. So tangent squared is secant squared minus 1. And secant squared y, well, secant y is x. So secant squared is x squared. And there it is. Why is it the same as the absolute value? Why is tangent y the same as absolute value of tangent y? Because by restricting your attention to the interval 0 to pi over 2 and pi to 3 pi over 2, then tangent y is positive. So tangent y is the same as absolute value of tangent y. And that's the reason for restricting your attention to these two intervals. 0 to pi over 2 and pi to 3 pi over 2. Well, the obvious question arises, what if we hadn't? What if we had taken these two intervals? Right? What if we had taken the two adjacent intervals? Then this would not have been true. This would have been true in the first interval, but then it would have been negative of that in the second one. So you would have broken it up into two pieces. Either that or it's negative, depending on whether tangent y was positive or negative. Everything would have worked out, but depending on whether tangent y is positive or negative, you would have had a plus or minus here. And you would have incorporated that into the x, turning it into absolute value x. Right? So what am I saying? I'm saying that if you are restricting your attention to these two intervals, the derivative of inverse secant is 1 over absolute value x. Square root of x squared minus 1. If you're restricting your attention to these two. If you're restricting the attention to these two, as the book does, no absolute value. So that's the difference. And, you know, if you pick up one book, some have the derivative of the inverse secant as this. If you pick up another book, they have the derivative of inverse secant as that. And so you're now confused as to which one is which and why do they have two different derivatives. That's because of the restriction of the domain of secant. Well, now that we've proven all of these in class, there's no need to go back. Let me give you the result. The derivative of inverse sine of x is 1 over square root of 1 minus x squared. The derivative of inverse tangent of x is 1 over x squared plus 1. And the derivative of inverse secant of x is 1 over x square root of x squared minus 1. Period. Here, with the understanding that you know which interval we are restricting our attention to. We're using Stewart. Stewart uses this, so that's what it is, period. Well, now the obvious question arises, what about the other 3 inverse trig functions? Namely inverse cos, inverse cotangent, inverse cosecant. Well, it's just the negatives of these respectively. So the derivative of inverse cosine is negative 1 over 1 by 7. Well, the derivative of inverse cotangent is negative 1 over x squared plus 1. The derivative of inverse cosecant is negative 1 over x square root of x squared minus 1. There it is. 6 new things to learn, but it's really just 3. And if you're really stuck, you could derive them yourselves. It's an important exercise. You should try this at home. Let's take some exercises from the book. Questions before we do so? Michael, let's not use the absolute value. Let's use this one. We want to be consistent. We want to be consistent with what the book is doing. So let's do that. All right, we're exactly that, Tina. If we're able to rewrite the derivatives as functions of x, it's always desirable to do so. And in this case, we could do that with relative ease. Consider this, we are looking for the derivative Why is that the case? Yusra, I'm not sure what case you're talking about. Tina? Michael's case? Or why we focus on the intervals we learn in class? I'm going to let you specify that. We'll come back to that. Looking for the derivative of this. Like, why is it negative? Well, so you mean these three derivatives? I'll let you work them out, right? If you're looking for the derivative of the inverse cosine function, so y is inverse cos. Take cosine of both sides. Cosine y is equal to x. And now you differentiate. Well, the derivative of cosine is negative sine. So you see where the negative is coming from. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. So you see where the negatives come from. It's not immediately clear that the denominators would be the same, but I'll let you work them out. You should work them out in exactly the same way we did. So what's the derivative? Well, what do we have? We have an inverse secant of something. So we differentiate the inverse secant first. Derivative of inverse secant is 1 over x square root of x squared minus 1. So 1 over e to the x, square root of e to the x squared minus 1, times the derivative of the inside. Chain rule, right? You saw that coming. Times the derivative of e to the x. These cancel out nicely, leaving you with 1 over the square root of e to the 2x minus 1. Shall I leave these up a bit more? Right, so again, just to be clear, we did not work these three out. You should do them in exactly the same way we did. Make sure that you get these answers. It's a great exercise. Everybody should do that at least once in their life. F of x is arctan of x squared. What's the derivative? Derivative of arctan. So 1 over x squared, the whole thing squared, plus 1, times the derivative of the inside, right? Chain rule again. Times 2x, or 2x over x to the 4, plus 1. Is everybody with us? Again, Maddie, we want to be consistent with the book, with what we're doing in class. So yes. If you want to define inverse secant, or if we are defining inverse secant on the exam, you understand that we have restricted secant to the intervals 0 to pi over 2 and pi to 3 pi over 2. Consider this. We want to differentiate. And what are we looking at? Here we have a product, x times arc cosine. So product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. What's the second one? It's arc cos of something. The derivative of arc cos -1 over the square root of 1 minus the something squared times the derivative of the inside. Derivative of root x, 1 over 2 root x. It's not 74, but rather 70. First any is asking for these types of problems. Will it also be specified, or we have, if you have to simplify? It should be specified. Here's what I suspect. For the midterm, I'm going to assume that you have to simplify everything. So unless otherwise stated, assume that you have to simplify everything. Tina is asking, how do we know when you have to do implicit versus explicit differentiation? It should be rather clear, right? I mean, the implicit differentiation only occurs when you don't have y equals some function of x, when you have an equation involving x's and y's. As we suggested, though, it actually doesn't matter, and the answer should be the same. But yeah. Consider this. What is the derivative? What is this? This is a how did we simplify to this? Well, I mean, it's a product rule, right? So it's a product, so we are applying the product rule. Derivative of the first one, leaving the second one fixed. Plus leave the first one fixed. Differentiate the second one, which is an arc cosine. So the derivative of arc cosine is -1 over the square root of 1 minus that thing squared. And then you have to differentiate the inside. The derivative of root x, we've done many times, 1 over 2 root x. And this is x to the 1/2, whose derivative is 1/2 x to the -1/2, which is what I have right here. Derivative of ln is 1 over. So 1 over arctan of t to the 4 times derivative of the inside. What is inside? Inside is an arctan whose derivative is 1 over this squared plus 1 times the derivative of the inside. Inside is t to the 4, whose derivative is 4t cubed. Exactly as suggested by Michael. Except not x squared, but rather t to the 4 all squared. And it's, Michael, it's not x squared, right? Or it's not t squared, but rather t to the 4. All right? Exactly, thank you. Shall we do one more? Now that you've committed these to memory, consider let's differentiate. You know how to differentiate. Right, what do we have here? This is a quotient. So quotient rule applies. VU prime. And what is this? Right, what is the derivative of u? What is u prime? This is a product. So product rule applies. So derivative of the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. Derivative of arc sine, 1 over square root of 1 minus x squared. Minus uv prime. So uv prime, derivative of sinus cos, all over sine squared, all over v squared. There it is. I won't simplify it, but you can if you wanted to. Questions here? Questions about the derivative of the inverse trig functions? Well, I mean, there's not much simplification to do, right? I mean, the only thing you could do, since you have a fraction in the numerator, you could put everything over a common denominator and bring the square root to the bottom. But that's it. Trivial indeed. Exam. We'll make it clear on the exam. Either we'll ask you to simplify completely, or we'll say you can leave your answer not simplified. Because, you know, sometimes the simplification doesn't bring much to the question, as in this case, and it's usually easier to see where a mistake would have gone wrong leaving it like this, right? If you leave it like this, it's clear that we were looking for a quotient rule and then a product inside the quotient rule kind of thing. So, yeah. And exactly, right? I mean, this simplification of this thing is really pre-calculus material. That being said, it is an important tool, and as you'll see very shortly, it's going to be important to simplify the derivative, because we'll be looking for where the derivative is 0, and in that case, it's going to be very important to get the simplest form of the derivative. Well, I mean, look, we're not looking to give 0 just because you've made a small mistake. If the derivative was correct, but simplification has gone wrong, you would expect some part marks. All right, let's move on. Let's move on to coming back to how we defined the derivative, right? We saw that the derivative gives you a rule to evaluate the slope of the tangent line, but we also saw that, right, I mean, the derivative is really the change in y divided by the change in x. And it's the behavior of this as the change in x gets smaller and smaller, closer and closer to 0, which is why we sometimes refer to the derivative as the instantaneous rate of change. So if we had a function which denotes the position of a particle, or position of a car, position of a person, the rate of change, how fast this particle changes position, how quickly the car changes position, the derivative of the position is the rate of change of the position, known as the velocity. That's a nice simple application to physics, absolutely, right? The derivative of the position is the velocity. Similarly, the rate of change of the velocity, how fast the velocity changes. The rate of change of the velocity is the acceleration. Let's consider a few examples from the book. If a ball is thrown vertically upwards with a velocity of 80 feet per second, then the height after t seconds is given by right, so the height after t seconds, or the position of the ball, is this. some questions arise naturally. What is the maximum height reached by the ball? And let's consider the scenario. You're throwing a ball upwards. Right? So imagine it going up. What's going to happen at the maximum height? Maximum height is when it stops coming up and starts going down. Exactly that, as Michael suggests, at the top height, the velocity is going to be 0. You're going to stop having a positive velocity, and it's going to start coming back down. So the height, or the position, is given as this. The derivative, which is the velocity, well, you know the derivative of this. What is the derivative? Easy to differentiate. 80 minus 32t. And this is the velocity. So when is the velocity equal to 0? This is easily seen to be, solve for t. T is 80 over 32. Or, can I divide by 8 here? 16, in fact. This is 5 times 16 over 16 times 2. 5 over 2, is that correct? So when t is 5 over 2, the velocity is 0. When t is 5 over 2, you have reached the highest point the ball is going to reach. So what is h of 5 over 2? When t is 5 over 2, what is the height? And that is 80 times 5 over 2 minus 16 times 25 over 4. So that's 200 minus 100, which is 100. 100 feet. 100 feet is, well, yes, of course, and as Nandini suggests, in these questions, the air resistance is not taken into account. But, yeah, so this is under perfect conditions, in a vacuum, if you will. But if your ball is small enough, you're probably close enough. I think we had a second question. What is the velocity of the ball when it is 96 feet above the ground? On the way up, and on the way down. So what is the velocity of the ball when it is 96 feet above the ground? Well, I mean, the obvious question arises, when is the ball 96 feet above the ground? Right? So when, at what time t, is the height equal to 96? For what value of t is the height equal to 96? If we bring everything to the other side, this is equivalent to asking for what values of t is this equal to 0? This is divisible by 4. 48, yeah. Why don't we factor out a 4 from there? So 4t squared minus 20t plus 24. I want to factor out another 4. 5t plus 6. And so we see that this factors nicely as t minus, does it factor nicely? T minus 3, t minus 2. So times 2 and 3. It was divisible by 16, thank you. Can we explain the manipulation of the equation for maximum height? We argued that, you're throwing a ball up in the air. The maximum height is going to be achieved when the velocity is 0. So we solved for the velocity being equal to 0, and we got the 5/2. And so 5/2 seconds in, at 2.5 seconds after having thrown the ball, you will achieve the maximum height, which is 100 feet. So at times 2 and 3, you are 96 feet above the ground. What is the velocity? Well, the velocity in general is the derivative of the position. So 80 minus 32t. So on your way up, at t equals 2, $80 minus 64, which is 16. The velocity is going to be 16 feet per second going up. On the way back down, the velocity at time 3 is 80 minus 96, which is negative 16. Same velocity, but going downwards. Same magnitude, exactly. Same magnitude, but with a negative because you're coming down this time. Same magnitude as expected, right? There it is. Very nice. Very nice indeed. Questions here? How are we doing? perhaps this is a good place to end if there are no questions. This is not on the midterm. As you know, the midterm ends with, where does it end? I want to say chain rule. Well, in fact, let me not say anything. I've posted the sections on my courses. Oh, indeed, there was no buffer. Interesting. Yeah. All right, so like I said, Wednesday is our last class before the midterm, before I release the midterm. So if you have questions, oh, you're right, I did not put Appendix D, but of course it is important. So I'll make that change. You are responsible for Appendix D, of course. Where did the 32t come from? It's the derivative. The velocity is the derivative of the position. So this was the position. Differentiate this. Derivative of 80t is 80. The derivative of 16t squared is 32t. You should write your work on paper for the midterm. You should write your work on the paper, take a picture, and upload it to CrowdMark. You will have the full 72 hours to do it. You can open it up, do some work, close it, come back to it. It's all good. Yep. All right. So thank you all for coming. And like I said, on Wednesday, if you have questions, material you want to go over, we can do that. Sean will be having a review session on Thursday. Details will be posted on my courses. So thank you all for coming, and I will see you on Wednesday.